The universe is about to put on its greatest show. We are living through a golden age of discovery where cosmic events once thought impossible are now predicted to happen within our lifetimes. By the end of this journey, you will know the 25 celestial spectacles that could redefine our place in the cosmos. We will witness stars dying in brilliant supernovas and sea probes sent to other stars. What single event do you believe will change humanity forever? Our own star is about to enter a period of violent activity. Scientists predict the Sun will reach its solar maximum around 2025, a peak in its roughly 11-year cycle of magnetic activity. This period, known as a grand solar maximum, could be one of the most intense in recorded history. The Sun's surface will become a chaotic tapestry of dark sunspots and erupting magnetic loops. From these turbulent regions, the Sun can hurl billion-ton clouds of superheated plasma directly at Earth. These coronal mass ejections are the most powerful explosions in our solar system. When such a storm is aimed our way, it triggers a celestial light show of epic proportions. Auroras, normally confined to polar regions, could dance in the skies over Rome, Tokyo, and even Mexico City. But this beautiful display carries a hidden danger. The same particles that paint the sky can induce powerful electrical currents in the ground. These currents surge through our long-distance power lines, threatening to overload transformers and cause widespread blackouts. Our fleet of satellites, which we rely on for communication and navigation, would be bombarded by radiation, potentially knocking them out of service for days or even weeks. We got a small taste of this in 1859 with the Carrington event, a solar storm so powerful it set telegraph offices on fire. A storm of that magnitude today could cripple modern infrastructure for months. This is not a distant possibility, but a real and impending test of our technological resilience. And as we look up at our turbulent Sun, we must also turn our gaze outward to a far more distant and far more destructive cosmic clock. That distant cosmic clock is ticking for a star you can see with your own eyes on any clear winter night. Look toward the constellation Orion, and you will find Betelgeuse, a red supergiant that glows with a distinct orange hue in the hunter's shoulder. This is no ordinary star. It is a dying leviathan, so vast that if it replaced our Sun, its outer atmosphere would stretch all the way to the orbit of Jupiter. And astronomers believe it is on the verge of a spectacular death. A supernova is the final, violent act of a massive star, a titanic explosion that outshines an entire galaxy. For Betelgeuse, this end is inevitable. The star is burning through the last of its nuclear fuel, its core a layered onion of progressively heavier elements, all building toward a catastrophic collapse. When that core can no longer support its own immense weight, it will implode in less than a second. The rebound from this collapse triggers an explosion of almost unimaginable power, blasting the star's outer layers into space at nearly the speed of light. The signs of this impending doom are subtle but detectable. Astronomers are watching Betelgeuse closely, monitoring its dramatic dimming and brightening as it pulsates, a sign of its unstable heart. They are searching for a telltale surge of neutrinos, ghostly particles that would flood from the collapsing core hours before the light of the explosion even reaches us. If it happens, the spectacle will be beyond anything humanity has ever recorded. A new point of light would appear in Orion, growing brighter and brighter until it rivals the full moon. It would be visible in broad daylight, a brilliant diamond in the sky, casting faint shadows at night for weeks or even months. The timeline, however, is the ultimate lesson in cosmic patience. Soon for a star like Betelgeuse could mean tonight, or it could mean 100,000 years from now. It is a reminder that the universe operates on a timescale we can scarcely comprehend, yet the anticipation is very real because we are the first generation with the technology to possibly witness such an event from its very first second. This stellar death would be a gift of cosmic knowledge, but it pales in comparison to a collision that has already been set in motion within our own galaxy. That collision already set in motion is a dance with a rock named Apophis. On Friday, April the 13th, 2029, this asteroid will race past our world, closer than some of our own weather and communications satellites. It will skim by at a distance of just 20,000 miles, a cosmic hair's breadth in the vast emptiness of space. Apophis is no small pebble. It is a mountain of space rock, over 1,000 feet across, and it will be moving at an astonishing speed of nearly 25,000 miles per hour. At that velocity and proximity, its passage is not just a close call. It is a historic event. For a short time, millions of people across parts of Europe, Africa, and Asia will be able to look up and see a fast-moving star gliding across the night sky, a silent reminder of the dynamic solar system we inhabit. The significance of this flyby cannot be overstated. While scientists have definitively ruled out any chance of impact for this pass and for the foreseeable future, Apophis represents a profound learning opportunity. It is a dress rehearsal for planetary defense. This is our chance to study a sizable near-Earth object with unprecedented detail, to observe how its trajectory is minutely altered by Earth's gravity, and to analyze its composition and structure. Every observation will sharpen our models and improve our ability to predict the paths of other, potentially hazardous asteroids in the future. This is not just a scientific curiosity. It is a crucial step in safeguarding our entire civilization. The data we gather from watching Apophis streak by will be invaluable, informing the technologies and strategies we may one day need to deflect a real threat. And as we track this nearby visitor, our attention is pulled to a far grander and more mysterious encounter, one that involves an entire world from another star. While we watch for known objects like Apophis, the true wildcards of our night sky arrive unannounced from the darkest reaches of our solar system. These are the comets, ancient icebergs of ice and rock that occasionally plunge toward the sun, and the race is always on to discover the next one that will become a naked-eye spectacle. Astronomers scan the skies nightly using powerful automated telescopes that capture thousands of digital images. They are searching for that one faint, fuzzy smudge that moves against the backdrop of stationary stars, a telltale sign of a new visitor. Most of these discoveries remain faint, visible only through large telescopes, but every so often we find one on a trajectory that promises a true celestial performance. A comet earns the title of great when it achieves two things. It must pass close enough to the Sun for its icy nucleus to erupt in a magnificent outburst of gas and dust, and it must also swing near enough to Earth for us to witness that brilliance clearly. When these conditions align, a comet can transform from a faint speck into a stunning apparition, its glowing head and vast, shimmering tail stretching across the heavens. We are long overdue for such a show. Think back to the great comets of the past century. Comet Hale-Bopp dominated the night sky for an incredible 18 months in the late 1990s, a steady and majestic guest. Comet Hyakutake, which arrived just a year earlier, stunned observers with a tail that stretched nearly halfway across the sky. These events were not just for astronomers. They were global phenomena witnessed by everyone, everywhere, a shared moment of cosmic awe. The next great comet could be discovered any day now. It might be lurking in the data from a sky survey at this very moment, its path being calculated, its potential being realized. When it comes, it will not require a telescope or a dark sky location. It will simply appear, a serene and silent visitor painting a streak of light across the twilight, a reminder of the beautiful and dynamic chaos from which our solar system was born. And as we anticipate this unpredictable visitor from our own solar backyard, we must also prepare for a planned encounter with a world that is utterly alien. The tools we use to witness these cosmic wonders are themselves evolving at a breathtaking pace. While the James Webb Space Telescope peers back toward the dawn of time, plans are already firmly in motion for its revolutionary successor. This next great observatory, currently known as the Habitable Worlds Observatory, is not merely an upgrade. It is a fundamentally different kind of instrument with a single, profound goal. It is designed to directly photograph and analyze Earth-like planets orbiting other stars. For the first time in human history, we will not be inferring the existence of these distant worlds. We will be pointing a telescope at another sun and seeing its family of planets as tiny, distinct points of light. The scientific ambition behind this mission is staggering. The primary mirror will need to be even larger than Webb's, a colossal eye gathering the faintest glimmers of light from unimaginable distances. But the real technological marvel will be an advanced instrument called a coronagraph, an internal mask that blocks the blinding glare of the parent star. This is like trying to see a firefly hovering right next to a massive spotlight from thousands of miles away. By precisely cancelling out the star's light, this observatory will reveal the faint, orbiting worlds we have so far only been able to detect through their subtle gravitational tugs or the tiny shadows they cast. The projected timeline sets a launch for some time in the 2040s. Once operational, its discoveries will utterly transform our understanding of the cosmos. It will not just find planets, it will study their atmospheres for the chemical signatures of life, the so-called biosignatures. It will look for key gases like oxygen and methane, which on Earth are produced almost exclusively by living organisms. Finding such a combination of gases on a rocky world within a star's habitable zone would be the strongest indication yet that we are not alone. This is the next logical and perhaps final step in a quest that has captivated humanity for millennia. We are building a machine capable of answering the ultimate question. Are there other Earths out there, and are they alive? This ultimate question of life beyond Earth will be answered by machines, but another profound step is being planned for humanity itself. We are on the cusp of leaving our cradle for good, with the first crewed mission to Mars now a matter of when, not if. Multiple space agencies and private companies have blueprints for this monumental journey, targeting the 2030-something decade. The architecture for such a mission is a masterpiece of logistics and survival. Imagine a spacecraft launching from Earth, but instead of heading straight for Mars, it first docks with a fuel depot in orbit. There, it fills its tanks for the long voyage ahead. The journey itself is a 9-month ordeal one way, trapped inside a small habitat with a handful of other people, watching Earth shrink to a pale blue dot. Upon arrival, the crew would not simply plant a flag and leave. They would live on the Martian surface for over a year, waiting for the planets to realign favorably for the return trip. This means a total mission duration of nearly 3 years. Every single aspect of this endeavor presents a staggering technological hurdle. How do you protect the crew from the constant, deadly radiation of deep space? How do you land a spacecraft heavy enough to sustain human life on a planet with a thin but substantial atmosphere? The solutions being tested are as ingenious as they are bold. SpaceX is developing its fully reusable Starship vehicle, a colossal rocket designed to carry up to 100 people and the immense amounts of cargo needed. NASA is working on advanced propulsion to shorten the travel time and robust habitats to shield explorers. The psychological challenge is just as immense. The crew will be the most isolated humans in history, with communication delays to Earth stretching to 20 minutes each way. They will have to be entirely self-sufficient, growing their own food in sealed greenhouses and recycling every drop of water. Yet, the historical significance of this step cannot be overstated. Setting foot on Mars would be the modern equivalent of the first ancient fish crawling onto land. It would mark the moment Homo sapiens officially became an interplanetary species, forever breaking the chains that have bound all life to this single world. This is not just an exploration, it is an insurance policy for the future of consciousness itself. And as we prepare to send the first pioneers to a new world, we are also developing the tools to listen more intently than ever before for neighbors we have not yet met. Finding that first whisper of life beyond our world will not be a single moment of revelation, but a slow, careful unraveling of data. A planet that today is just a number in a catalog will suddenly become the most fascinating place in the universe because its atmosphere will tell a story we have never heard before. The key to this story lies in biosignatures, which are simply chemical imbalances that are incredibly difficult to explain without the presence of life. Think of Earth as seen from a distant telescope. An alien astronomer would detect an atmosphere rich in oxygen, a gas that is highly reactive and should quickly vanish by bonding with rocks and minerals. The only reason it persists here in such large quantities is that life, primarily plants and phytoplankton, constantly pumps it back into the air. They would also see methane, a gas that sunlight breaks down rapidly. Its continued presence suggests an active source, much of which on Earth comes from living organisms like bacteria and animals. Finding oxygen and methane together is the gold standard because they destroy each other. To have both present in an atmosphere means something on that world is continuously replenishing them. That something is almost certainly biology. The discovery of such a combination on a rocky planet within its star's habitable zone would send shockwaves through every field of science and philosophy. It would mean that the recipe for life is not a rare, one-off fluke confined to our little world, but a common ingredient in the cosmic kitchen. The implications are so profound they are difficult to fully grasp. Our entire perspective on existence would shift overnight. We would no longer be a solitary miracle, but one voice in a cosmic chorus. Every star in the night sky would become a potential sun for another living world. This discovery would redefine our place in the universe, not as its center, but as a part of a vast and likely teeming biological fabric. This new outpost will not circle the Earth, but the Moon itself. The Lunar Gateway represents a fundamental shift in how we approach space exploration, a permanent space station designed to orbit our celestial neighbor. This international endeavor, led by NASA alongside partners like the European Space Agency, the Canadian Space Agency, and JAXA, is more than just a habitat. It is a strategic port, a science lab, and a fuel depot all rolled into one. Its primary purpose is to enable sustainable lunar exploration. Unlike the Apollo missions, which were direct flag-planting sprints, the Gateway allows for a marathon approach. Astronauts will travel from Earth to the Gateway, using it as a base camp before descending to the lunar surface in a dedicated lander. This modular system means we can go back to the Moon again and again, building a lasting presence. The station's orbit is itself a marvel of engineering, a highly elliptical path that brings it incredibly close to the lunar surface at one point and then far out into cislunar space at another. This unique trajectory provides unparalleled access to the Moon, while also serving as the perfect jumping-off point for missions deeper into the solar system. Imagine a spacecraft launching from Earth with minimal fuel, docking at the Gateway to refuel from a dedicated depot, and then using the Moon's gravity to slingshot toward Mars. This turns the Gateway into the first interplanetary transit hub, a bustling crossroads for all future deep space travel. The assembly of this orbital outpost is set to begin in the coming years, with the first modules launching as early as 2025. Over several subsequent Artemis missions, the station will grow, piece by piece, into a fully functional complex. Its completion, projected for the early 2030s, will mark the moment humanity truly became a multi-world species with a permanent address beyond our home planet. It is the foundational stone upon which we will build our future among the stars. The silent void between galaxies holds the potential for the most violent explosions since the Big Bang. These are gamma-ray bursts, and statistically, one is due to occur in a galaxy not too far from our own. These are not mere stellar explosions. A single gamma-ray burst, lasting from a few milliseconds to several minutes, can release more energy than our Sun will emit over its entire 10 billion-year lifetime. It is a focused blast of pure radiation, a lighthouse beam of death concentrated into two narrow jets erupting from the poles of a collapsing star or merging neutron stars. For any world caught in the crosshairs of such a beam, the consequences would be apocalyptic. If one were to originate within a few thousand light years of Earth and point directly at us, the initial flash of gamma rays would deliver a direct blow to our upper atmosphere. It would rip electrons from air molecules, creating a cascade of chemical reactions that would rapidly deplete the ozone layer, our planet's essential shield against the Sun's ultraviolet radiation. The sky would literally sizzle. The aftermath would be a slow-moving catastrophe. With our protective ozone layer shredded, lethal levels of ultraviolet light would pour onto the planet's surface, devastating ecosystems on land and in the oceans. It would trigger a mass extinction event, not with fire and impact, but with an invisible, sterilizing rain from the sky. Fortunately, the odds of such a direct hit are astronomically low. The vastness of space is our greatest shield, yet the statistical certainty of a nearby burst remains. Astronomers are not taking any chances. A global network of telescopes, both on the ground and in space, constantly scans the heavens for these fleeting, brilliant events. Satellites like NASA's Swift and Fermi observatories are our early warning system, designed to detect the initial flash of gamma rays and instantly relay its coordinates to observatories around the world. They watch for the telltale afterglow, a fading beacon of light across other wavelengths that reveals the burst's origin and distance. Each detection is a data point in a cosmic ledger, helping us understand the frequency and distribution of these ultimate cosmic bombs. We are living in an era where we can witness these titanic events from a safe distance, learning their secrets while respecting their power. It is a sobering reminder that the universe is not just beautiful, it is also unimaginably fierce. This same cosmic clockwork that governs stellar explosions also choreographs a far more serene event right here in our own solar system. Every so often, the planets, each moving at its own pace along its orbital lane, fall into a beautiful alignment from our earthly perspective. We call this a grand conjunction, a gathering of worlds in a small patch of the night sky. The mechanics are a dance of timing and geometry. The inner planets, like Mercury and Venus, race around the Sun in weeks or months, while the outer giants, like Jupiter and Saturn, take decades. A grand conjunction occurs when several of these independent orbits bring the planets into the same line of sight, making them appear as a brilliant, tight-knit family of stars. The next truly spectacular alignment is already on the calendar. Mark the date of June 12, 2040. On that evening, just after sunset, look toward the western horizon. There you will witness a rare celestial meeting. Mars, Venus, Mercury, and Jupiter will all be clustered together within a circle of sky no larger than the width of your thumb held at arm's length. The sight will be breathtaking. Venus will shine with its familiar, steady brilliance, while Mars will glow with a distinct, rusty hue. Jupiter will be a bright, creamy beacon, and the elusive Mercury will twinkle close to the horizon. You will not need a telescope to appreciate this event. Simply find a clear view to the west, free from trees and city lights, and the planetary quartet will be plainly visible to your naked eye. It is a direct personal connection to the clockwork of our solar system, a demonstration of gravitational harmony playing out on a scale we can actually see. For a few magical hours, the vast distances between these worlds will seem to collapse, offering us a perfect miniature portrait of our celestial neighborhood. The first single image of the black hole M87 star was a monumental achievement, but it was a single frame in a cosmic motion picture. Now, the global collaboration known as the Event Horizon Telescope is attempting the impossible, to stitch together those frames and create the first movie of a black hole. The target is the same supermassive giant, a gravitational monster with the mass of 6.5 billion suns. The goal is to witness its accretion disk, that swirling vortex of superheated gas and dust, not as a static halo, but as a dynamic, churning whirlpool in real time. Capturing this motion presents a challenge that dwarfs even the initial photograph. The Event Horizon Telescope is not one single instrument, but a network of radio observatories scattered across the globe, from the high deserts of Chile to the frozen peaks of Hawaii. To create a movie, these telescopes must all observe the black hole simultaneously, night after night, for multiple years. They are essentially turning the entire planet into a single, colossal camera with a lens as wide as Earth itself. Every night of observation adds another precious frame to the sequence. The technical hurdles are almost beyond comprehension. The data from each observing run is so vast it cannot be sent over the internet. It has to be physically shipped on hard drives to central processing centers. Scientists then spend years correlating the signals, a painstaking process of aligning the faint whispers of radio waves captured by each telescope to reconstruct a coherent image. To turn this into a movie, they must repeat this entire arduous process for multiple epochs of observation. What will this moving picture reveal? We will no longer see a blurry, static ring. We will see the accretion disk itself evolve, witnessing blobs of plasma whip around the event horizon at near light speed. We might see the entire ring wobble and flicker as magnetic fields twist and snap. This is not just about watching gas move. It is about testing Einstein's theory of general relativity in the most extreme environment imaginable. We will see how spacetime itself is dragged around by the black hole's insane rotation, a phenomenon known as frame dragging. A successful movie would be the ultimate proof that we are not just looking at a picture, but truly observing the violent, dynamic physics at the edge of reality. It would transform a cosmic icon into a living laboratory, and as we push the limits of observation to their absolute extreme, we must also prepare for a moment when our own planet becomes an observatory for a different kind of celestial clockwork. Far beyond the orbit of Neptune, in the cold, dark reaches of our solar system, a ghost is pulling on the strings of reality. Astronomers call it Planet 9, a hypothetical world so massive it could be 10 times the weight of Earth, and yet it has never been seen. The evidence for its existence is not a direct photograph, but a trail of gravitational breadcrumbs left by smaller, icy bodies. These are the Kuiper Belt objects, frozen remnants from the solar system's birth, and their orbits tell a bizarre and consistent story. They do not scatter randomly. Instead, their elongated paths are mysteriously clustered, as if an unseen shepherd is herding them, guiding their trajectories with an immense and distant gravitational hand. This orbital oddity is the primary clue. The chances of this clustering happening by pure chance are astronomically low, less than 1 in 10,000. Something out there, something big, is orchestrating this cosmic dance from the shadows. The search for this phantom planet is one of the greatest modern astronomical detective stories. Teams of researchers are using the world's most powerful telescopes, like the Subaru telescope in Hawaii, to scan vast swaths of the sky. They are not looking for a bright, obvious disk, but for a faint, slow-moving dot, a world so far from the sun it would reflect only the faintest glimmer of starlight. Its orbit is predicted to be incredibly long, taking perhaps 10 to 20,000 years to complete a single journey around the sun. Finding it is like searching for a single, specific grain of black sand on a pitch-black beach at midnight. What would the discovery of Planet 9 mean for us? It would be a revolution in planetary science, a complete rewrite of our solar system's family portrait. For centuries, we have operated under one model of our cosmic neighborhood, only to have it upended time and again. The demotion of Pluto was a minor adjustment compared to this. Finding a new giant planet would force us to reconsider everything we thought we knew about how planetary systems form and evolve. How did it get there? Was it an exiled giant kicked out from the inner solar system in a long-forgotten gravitational tussle with Jupiter or Saturn? Or is it a rogue world captured from another star that passed by in the solar system's infancy? Its discovery would not just add a new world to our charts. It would unveil a hidden chapter in our own history, a dramatic past of planetary billiards and cosmic theft that we never knew existed. This hidden giant reminds us that our exploration of the solar system is far from over, and that the most profound discoveries may still be lurking in the darkness just beyond our sight. While we map the distant darkness for hidden worlds, a far more immediate spectacle is brewing within our own celestial neighborhood. A major meteor shower outburst promises to turn our night sky into a temporary blizzard of light. This is not the gentle, predictable sprinkle of a typical shower. This is a meteor storm, an event where rates could explode from a few dozen per hour to hundreds or even thousands, streaking across the sky every 60 seconds. The cause is a celestial traffic jam of the most beautiful kind. Meteor showers happen when Earth, on its yearly orbit, plows through the scattered debris trail left behind by a comet. These particles, often no larger than grains of sand, vaporize in our atmosphere, creating the swift, bright streaks we see. An outburst occurs when our planet's path intersects an unusually dense and concentrated ribbon of this debris, one that was shed by the comet during a specific pass hundreds of years ago. Think of a comet's orbit as a dirt road with fresh piles of gravel dumped at different points along the way. In a normal year, we might drive through a light dusting. But during an outburst, we hit one of those specific ancient gravel piles head-on. The most famous candidate for such a storm is the Leonid shower, which peaks every November. Its parent comet, Tempel-Tuttle, swings by the inner solar system roughly every 33 years, and its concentrated dust trails have been known to produce legendary storms. In 1833, a Leonid storm was so intense it was described as a snowfall of fire, waking people across North America and sparking religious fervor. The next potential outburst could happen when our orbit precisely intersects one of these dense filaments. To witness such an event, you need no special equipment, only patience and a dark sky. Find a location far from city lights, allow your eyes at least 20 minutes to adjust to the darkness, and lie back on a blanket or reclining chair, looking generally upward. The key is to take in the whole sky, not just one spot. While the meteors will appear to radiate from a single point, they can flash anywhere overhead. The best time is always after midnight, when your location on Earth is facing forward into the planet's direction of travel, like the front windshield of a car driving through a snowstorm. This simple act of looking up could reward you with a memory that lasts a lifetime, a front row seat to the dusty remains of a comet, painting the atmosphere with fleeting, brilliant strokes. The silent, stately dance of our galaxy is leading to a final, breathtaking embrace. Our Milky Way is on an irreversible collision course with its nearest giant neighbor, the Andromeda Galaxy. This is not a possibility, but a certainty dictated by gravity, a slow-motion car crash set to unfold over billions of years. For now, Andromeda is a faint, fuzzy smudge in our autumn sky, a tranquil island of stars. But as the eons pass, that smudge will grow, swelling from a faint patch into a brilliant, structured spiral hanging in the night. The approach will be deceptively graceful, a celestial ballet where the two galaxies, drawn together by their immense mutual gravity, slowly close the 2.5 million light-year gap between them. In the final hundreds of millions of years before impact, the night sky will transform into something utterly alien and magnificent. The Andromeda Galaxy will dominate the heavens, its spiral arms stretching across a vast portion of the sky, a second, ghostly disk of stars superimposed over our own. As the galaxies begin their first pass, they will not smash head-on like two cars. Their stars are so widely spaced that they will simply slide through one another, a ghostly intermingling. The real violence will be reserved for the galaxies themselves. immense tidal forces, the same gravitational pull that the moon exerts on our oceans but on an unimaginable scale, will warp and stretch both spiral disks. Long, streaming arms of stars, gas, and dust will be ripped away, forming colossal bridges and tails that arc across the cosmos. Through it all, the view from Earth would be a chaotic, beautiful nightmare. The familiar band of the Milky Way would be torn asunder, its structure lost amidst a sky now filled with double the number of stars. New star-forming regions would ignite like cosmic fireworks as clouds of gas collided and compressed, birthing brilliant blue clusters and lighting up the dark nebulae. The core of the Andromeda Galaxy would blaze as a second, intensely bright hub of light opposite our own galactic center. This dramatic dance will not be a single event, but a series of close passes over billions of years. The two galaxies, now hopelessly entangled, will fall back toward each other and finally merge into one. The resulting object, a vast, elliptical galaxy that astronomers have nicknamed Milkomda, will be a featureless, golden-hued swarm of stars. The elegant spiral structures of its parents will be gone forever, erased by the gravitational turmoil. All that will remain is a calm, spherical island of aging suns. For any life that exists then, the night sky will be profoundly different, devoid of the grand spiral we know today, a permanent monument to a cosmic union that reshaped the heavens. The silent tremors of colliding black holes are about to become a symphony we can finally hear. While our ground-based observatories have given us the first fleeting whispers of these cosmic ripples, a new generation of instruments is poised to launch our listening capabilities into an entirely new realm. The Laser Interferometer Space Antenna, or LISA, is not just another telescope. It is a gravitational wave observatory that will float in the void of space, a trio of identical spacecraft flying in a perfect triangular formation millions of miles apart. Their mission is to detect the faintest wobbles in spacetime itself, distortions caused by the most cataclysmic events in the universe. Think of it like this. If you drop a pebble into a still pond, ripples spread outward. A supermassive black hole merger is like dropping a mountain into that pond. The ripples it creates are gravitational waves, stretching and compressing the very fabric of reality as they travel at the speed of light. Our current detectors on Earth are like sensitive fingers trying to feel those ripples in a shallow, choppy puddle, constantly disturbed by seismic rumbles and passing trucks. LISA, by operating in the pristine quiet of space, will be like listening from the deep, calm center of the ocean. It will be tuned to hear the low-frequency waves that are completely inaccessible from the ground, the deep, resonant chords of the cosmos. This will open a window onto events we have never directly witnessed. We will hear the final, spiraling dance of supermassive black holes as they orbit each other for millions of years before their final, universe-shaking collision. These are the true giants lurking at the hearts of galaxies, and their mergers are the most energetic events since the Big Bang. Traditional telescopes see nothing, for no light escapes the chaos. But LISA will hear it all, translating the warping of spacetime into a data stream that tells us the masses, spins, and distances of these invisible monsters. It will allow us to census the population of supermassive black holes across the universe, understanding how they grow and shape the galaxies around them. We might even hear the faint echo from the very first seconds after the universe began, a primordial whisper from the dawn of time. With LISA, we are not just building an observatory. We are giving the cosmos a voice, and we are finally ready to listen to its deepest, most powerful secrets. Stored inside a small, sterile tube on the surface of Mars is a piece of another world, carefully sealed by a robotic geologist. This is the heart of the most ambitious interplanetary project ever attempted, the Mars Sample Return Campaign. Right now, NAS, a Perseverance rover, is traversing the ancient river delta of Jezero Crater, a place scientists believe was once filled with water. Its mechanical arm, equipped with a sophisticated drill, is coring into rocks and collecting pristine, pencil-thin samples of Martian regolith. Each sample is a time capsule, potentially holding secrets from an era when Mars was a warmer, wetter planet that might have been hospitable to life. Perseverance does not analyze these rocks itself. Instead, it carefully seals them inside ultra-clean tubes and leaves them in a designated cache on the surface, a treasure chest waiting for a future mission to retrieve it. This next phase is where the plan becomes a breathtaking feat of cosmic logistics. A separate mission, a collaboration between NASA and the European Space Agency, will launch later this decade. It will consist of two main components, a lander and an ascent vehicle. The lander will touch down perilously close to the sample cache, and a small fetch rover built by ESA will roll out, locate the tubes, and gather them up. This rover will then return to the lander and load the precious cargo into a container about the size of a basketball, which sits atop a small, innovative rocket, the Mars Ascent Vehicle. This is the moment of truth, a launch from the surface of another planet. The Mars Ascent Vehicle will ignite its engines and fire the sample container into Martian orbit, a first in human history. But the journey is only half over. Waiting in orbit will be a third spacecraft, the Earth Return Orbiter, also provided by ESA. It must rendezvous with this tiny, speeding container, capture it with a sophisticated mechanism, and then seal it inside a robust, biocontained capsule for the long voyage home. The entire timeline, from Perseverance's first sample to the canister's fiery re-entry into Earth's atmosphere, is projected for the early 2030s. The scientific payoff will be nothing short of revolutionary. In laboratories on Earth, scientists will have the chance to study these rocks with instruments far more powerful and precise than anything we can send to Mars. They will search for microscopic fossils or chemical traces of ancient microbial life, seeking definitive proof that we are not alone in the universe. They will analyze the rocks to understand the precise geological and climatic history of Mars, learning why it became the cold desert it is today and what that might mean for the long-term future of our own world. This is not just about bringing back rocks, it is about bringing back answers to questions that have haunted humanity for centuries. This silent listening will soon be amplified by the most ambitious ear ever pointed at the cosmos. The square-kilometer array is not a single telescope, but a vast network of antennas, a forest of metal and wire being planted across the remote landscapes of South Africa and Western Australia. When its final component is switched on, this colossal instrument will become the most sensitive radio telescope in human history, capable of detecting an airport radar on a planet orbiting a star tens of light years away. Its sheer scale is difficult to comprehend. The name itself refers to its total combined collecting area, a full square kilometer of listening surface spread out over thousands of individual dishes and millions of smaller antennae. This distributed design allows it to scan the sky with a speed and clarity that is simply impossible for any other instrument. Its primary mission is to listen back to the very beginning of everything. The SKA will tune its receivers to a specific, faint radio whisper emitted by neutral hydrogen gas. This signal is a cosmic timestamp, and by mapping its faint red-shifted echo, the telescope will be able to create a three-dimensional movie of the universe's infancy. We will watch as the first stars and galaxies flicker to life, burning away the cosmic fog of the dark ages and flooding the cosmos with their first light. This is a journey to our own cosmic dawn, but its gaze will also turn outward, searching for the one signal that would change everything. The SKA is so sensitive it could detect leakage radiation from an alien civilization, the equivalent of picking up their television broadcasts if such a thing exists. It will systematically scan millions of star systems, listening for the faint, artificial pulse of a transmission that nature could never produce on its own. Beyond this search for origins and neighbors, the telescope will perform a cosmic cartography of staggering precision. It will map the filamentary structure of the cosmic web, the vast, invisible scaffolding of dark matter upon which all the galaxies are strung. It will watch pulsars, the spinning corpses of dead stars, to detect the background hum of gravitational waves washing through our galaxy. Every observation will be a step into the unknown, probing fundamental physics and the history of the cosmos with a power we have only just begun to imagine. The activation of the full array, projected for the late 2020s, will mark the start of a new epoch in astronomy, one where the universe's quietest secrets are finally brought into the light. Deep within the static hiss of the cosmos, a secret message has been repeating for years. Fast radio bursts are among the most perplexing signals we have ever detected, brilliant flashes of radio waves that erupt with the power of 500 million suns, yet they last for barely a few milliseconds. Most appear as one-off events. Cosmic lightning strikes that flash and are gone forever. But a handful of them, the repeating fast radio bursts, defy this pattern. They flare up again and again from the same patch of sky, a persistent, energetic beacon that refuses to be ignored. This repetition is the key that may finally unlock their origin. With each new pulse from a source like FRB 121110-2, our most powerful radio telescopes like the CHIME array in Canada gather more clues. They are triangulating the signal's location with ever greater precision, not just to a galaxy, but to a specific neighborhood within that galaxy. The leading theory points to an incredibly dense, highly magnetized neutron star known as a magnetar. Imagine a stellar corpse with a magnetic field so powerful it could erase a credit card from halfway across the solar system. The thinking is that starquakes on the surface of such an object, or sudden reorganizations of its intense magnetic field, could crack like a cosmic whip, releasing these titanic bursts of energy. But the mystery deepens with more exotic proposals. Some scientists speculate that these repeating bursts could be power signatures from incredibly advanced technology. Could a civilization be focusing immense energy to propel light sails on interstellar voyages, with each burst a momentary flash from their engine? Or are we witnessing something even stranger, like the violent evaporation of primordial black holes? The prediction is that within the next few years, as next-generation telescopes like the Square Kilometre Array come online, we will not just locate a repeater's home, we will see what is right next to it. Is it nestled in a turbulent star-forming region, supporting the magnetar theory? Or is it isolated in the quiet, dark voids between stars, suggesting something far more unusual? Solving this puzzle is not just about cataloging a new type of celestial object. It is a fundamental test of physics in the most extreme environments imaginable, and a search for answers to the most profound question of all. Are we listening to the death cries of stars or the engineering signatures of intelligence beyond our own? The silence of orbit will soon be broken by a new kind of human outpost. For the first time in history, the construction of a commercial space station is not a concept, but a tangible reality taking shape in factories on Earth. Companies like Axiom Space are leading this charge with a clear and ambitious plan. Their station will not be built all at once, but will grow organically, starting with a series of private modules designed to dock directly with the International Space Station. The first of these modules is scheduled to launch and attach to the ISS as early as 2026. This initial phase is a crucial proving ground, allowing the company to test its systems and host its first private astronauts and research customers while still connected to the power and safety of the established station. But this is only the beginning. After several years, once the full suite of Axiom modules is in place and operational, the entire new segment will detach from the aging ISS. It will then fire its own thrusters and maneuver away, becoming a fully independent, freely flying private station in low Earth orbit. This is the birth of a true commercial neighborhood in space. So what will people do there? The uses are as varied as they are revolutionary. Space tourism will evolve from brief visits to extended stays, where private citizens can live and work in orbit for weeks at a time. But the real promise lies in the unique environment of microgravity itself. Pharmaceutical companies plan to grow perfect protein crystals for drug development, a process impossible to replicate on Earth. Manufacturers will develop new alloys and flawless fiber optics, materials whose structures are ruined by gravity's constant pull. The station will become a high-tech laboratory, a factory, and a hotel all rolled into one. This marks a fundamental shift in how we operate in space. For decades, access to orbit has been the exclusive domain of governments. The success of these commercial stations will open the floodgates, creating an economy in space for Earth. It transforms space from a destination only for explorers and scientists into a domain for entrepreneurs, artists, and innovators. The final separation of that first private station will be a quiet but monumental event, signifying that humanity's future in space will not be a solitary government-led endeavor, but a vibrant, collective, and commercial enterprise. That first photograph of another Earth will be more than an image. It will be a revelation, a moment that carves a new chapter into human history. For centuries, we have inferred the existence of these distant worlds through shadows and wobbles, but to finally see one as a distinct point of light is a challenge that pushes our engineering to the absolute limit. The central problem is one of contrast. A star is a raging inferno, while a planet is a cold, dark ember orbiting it. Trying to see the planet next to its star is like trying to spot a single glowing firefly hovering directly against the blazing beam of a lighthouse from 10,000 miles away. The light from the star completely overwhelms the faint reflection from the world. To solve this, astronomers are building instruments with a kind of cosmic coronagraph, an internal mask that precisely blocks the star's light after it enters the telescope. This is not a simple piece of metal. It is an active, shape-shifting system that cancels out the starlight with wave-like precision, allowing the million times fainter light of the planet to finally emerge from the glare. Missions like the Habitable Worlds Observatory are being designed from the ground up for this single, monumental task. Their mirrors must be so smooth, so perfect, that if they were scaled to the size of North America, their largest imperfection would be the height of a small pebble. This is the level of precision required to bring that pale blue dot into focus. When it happens, the data will not arrive as a beautiful, full-color portrait immediately. At first, it will be a single pixel, a single point of light in the vast blackness. But that one pixel will contain a universe of information. By splitting its light into a spectrum, we will be able to read the chemical composition of its atmosphere. We will search for the telltale signs of water vapor, for the unmistakable red edge of vegetation, and for the chemical imbalances like oxygen and methane together that shout the presence of life. Seeing that first pale blue dot will be a profound echo of the famous photograph of our own Earth taken from the edge of our solar system. It will collapse the cosmic distance, transforming abstract points on a graph into a place. A world with its own seasons, its own oceans, and potentially its own inhabitants looking back out into the silence. That single point of light will answer one ancient question, while igniting a million new ones about our place in a universe that may be filled with neighbors. That first photograph of another Earth will redefine our world, but we need not look so far to find a landscape forged in celestial fire. A world of perpetual violence awaits in our own cosmic backyard, orbiting the giant planet Jupiter. Its moon Io is a vision of hellish beauty, the most volcanically active body in the entire solar system. Its surface is a chaotic canvas of yellow, red, and black, painted by hundreds of active volcanoes constantly spewing molten rock and sulfurous gas into its thin atmosphere. This is not the sporadic volcanism we see on Earth. Io is a world in a state of constant global eruption, where lava flows can stretch for hundreds of miles and plumes of volcanic debris are routinely blasted hundreds of miles high, raining back down to coat the tortured surface. The scale is almost incomprehensible. An eruption on Io is not a single mountain letting off steam. It is a planetary scale event with individual volcanic centers larger than entire cities. The energy powering this relentless fury does not come from a radioactive core as it does on our planet. Io is caught in an unending gravitational tug-of-war. As it orbits Jupiter, the immense gravity of the giant planet, combined with the rhythmic pulls from its sister moons Europa and Ganymede, constantly squeezes and stretches Io's interior. This process, known as tidal heating, generates immense friction, turning the moon's insides into a roiling ocean of magma. It is as if the entire world is being kneaded like dough, its internal heat stoked to a breaking point over and over again. Predicting the next major eruption here is a priority for missions like NASA's Juno spacecraft, which regularly swoops past Io to monitor its volcanic tantrums. A truly colossal event could happen at any moment, an eruption so large it would be visible from Earth-based telescopes as a brilliant hotspot on the moon's disk. Studying these outbursts is more than just observing a spectacle. Io serves as a natural laboratory for understanding the extremes of planetary geology. It shows us how tidal forces can sculpt worlds, providing a key to unlocking the potential for hidden, liquid water oceans on moons like Europa and Enceladus, where that same tidal heating occurs under a frozen crust. By watching Io's fire, we learn about the possibilities for life in the icy shadows. This violent moon is a stark reminder that a world does not need to be in a star's habitable zone to be intensely, dynamically alive. This ambition to touch another star requires a machine unlike any we have ever built. Forget the massive, nuclear-powered probes of the past. The future of interstellar travel is microscopic. The most daring plan is Breakthrough Starshot, a project that envisions sending a fleet of gram-scale probes, each no larger than a postage stamp, to our nearest stellar neighbor, Alpha Centauri. These would be spacecraft on a chip crammed with tiny cameras, sensors, and communication equipment. The concept is simple in theory but borders on science fiction in its execution. The propulsion system would not be rockets but light itself. Each tiny probe would be equipped with an ultra-thin, highly reflective light sail, a sheet of material only a few atoms thick. Back on Earth, a vast array of powerful ground-based lasers, combining their beams into a single, immense push, would target these sails. For a few minutes, this laser phalanx would fire, bathing the sails in a concentrated beam of light with the power of a small nuclear reactor. The photons, though massless, carry momentum, and this constant pressure would accelerate the tiny probes to an almost inconceivable velocity, 20% the speed of light. At that pace, the journey to Alpha Centauri, a distance of 4.37 light-years that would take our current spacecraft tens of thousands of years, would be reduced to a mere 20-year cruise. Imagine these silent, glinting specks, a swarm of cosmic dust, coasting through the interstellar void for decades. Upon arrival, their miniature instruments would spring to life, taking a frantic series of images and measurements as they scream past the alien planets of that system at blistering speed. Then comes the final, incredible challenge, beaming that precious data all the way back to Earth using a tiny, onboard laser. It would be a whisper from another star, a message taking over 4 years to reach us, carrying our first direct postcards from another sun. This is not a mission for one generation to complete, but a gift from ours to the future, a proof that humanity's curiosity can finally reach beyond the gravitational well of our own sun. The echoes of colliding black holes are powerful, but they are mere whispers compared to the deep, foundational hum we now seek. This is the hunt for primordial gravitational waves, the faintest ripples in the fabric of space-time, generated in the first trillionth of a second after the Big Bang. Detecting them would be like finding the original fingerprint of creation, a direct imprint from the universe's violent birth. These waves are not from stellar collisions, but from the event of cosmic inflation itself, a theory proposing that the entire cosmos underwent a period of unimaginably rapid expansion, ballooning from a subatomic speck to something macroscopic in less than a blink of an eye. This explosive growth would have sent shockwaves through the very structure of reality, ripples that have been stretching and fading across the cosmos for nearly 14 billion years. The challenge of finding them is monumental. These primordial waves are now incredibly long and weak, their signal buried in the faint, ancient light that fills the universe, the cosmic microwave background. This afterglow of the Big Bang is our oldest photograph of the cosmos, and hidden within its subtle patterns of polarization, like the specific alignment of light waves, may be the telltale swirls and curls imprinted by those first gravitational tremors. Next-generation observatories are being designed with this single goal in mind. Missions like LightBird and the Simons Observatory will scan the entire sky from the pristine environment of space or the high, dry plateaus of Chile, using ultra-sensitive detectors to map the cosmic microwave background with a precision we have never before achieved. They are looking for a specific pattern, a unique curling in the polarization that can only be caused by gravitational waves shaking the fabric of space-time in those first instants. Finding this signal would do more than just confirm a theory. It would open a window to a time before time, as we understand it, began. It would tell us about the energy scales and the fundamental forces that were unified at that moment of ultimate energy. We would, for the first time, have empirical evidence of what the universe was like when it was 1 trillion times hotter than the core of our sun, and all of reality was compressed into a single point. This is not just astronomy, it is a form of cosmic archaeology, digging back to the very first moment everything began, listening for the echo of existence itself. The moon's shadow is about to race across the face of the Earth, and on April 8, 2024, it will plunge a vast swath of North America into an eerie and sudden twilight. This is the Great American Eclipse, a total solar eclipse whose path of totality will sweep from Mexico, across the United States from Texas to Maine, and into the Canadian Maritimes. For those standing directly in the center of this path, the show will last for up to 4.5 minutes, a fleeting window into one of nature's most profound spectacles. The experience begins subtly. A partial eclipse is interesting, a crescent sun casting strangely sharp shadows. But as the moon encroaches further, the world begins to change in unsettling ways. The quality of the light becomes metallic and wan, the temperature drops noticeably, and the wind may pick up. Animals grow confused, with birds falling silent and returning to their nests as if night has arrived hours early. Then comes the final, breathtaking moment. The last sliver of the sun vanishes and totality begins. The sky turns a deep twilight blue, and the sun's outer atmosphere, the corona, erupts into view. It is a shimmering, pearly white halo, with delicate, feathery streamers stretching outwards for millions of miles into the blackness of space. Around the black disk of the moon, you might see ruby-red prominences, immense loops of plasma arcing from the sun's surface. Bright stars and planets appear in the middle of the day, with Venus and Jupiter flanking the darkened sun. This is not a mere astronomical event, it is a full-body experience that defies description. The sight evokes a primal awe, a feeling of being a tiny part of a vast and precise cosmic mechanism. People scream, they cry, they laugh in disbelief. For those few minutes, differences vanish as thousands of strangers stand together, united under the darkened sky, sharing a moment of pure, unadulterated wonder. This eclipse will be one of the most witnessed in history, its path crossing major cities and densely populated regions, ensuring millions will have a front-row seat. It is a celestial reminder of our shared place on this fragile planet, a fleeting alignment that connects us directly to the clockwork of our solar system. Beneath the frozen, cracked crust of a distant moon, an entire ocean is waiting to be discovered. This is not a scene from science fiction, but the scientific reality of worlds like Jupiter's Europa and Saturn's Enceladus. These are not barren balls of ice. They are active, dynamic worlds hiding vast, global seas of liquid water under their surfaces, and we are on the verge of sailing into their depths. The evidence is already stunningly clear. We have seen the giant plumes of water vapor and ice crystals erupting from Enceladus's south pole, a cryovolcanic geyser shooting material hundreds of miles into space. We have mapped the chaotic, jumbled terrain on Europa's surface, a clear sign of a churning ocean below constantly breaking apart and refreezing the icy shell above. These are not quiet, dark abysses. They are likely tidal heated environments with energy sources and liquid water, the two key ingredients for life as we know it. The next step is to go there and taste the water. Missions like Europa Clipper and the proposed Dragonfly rotorcraft to Titan are not just orbiters and landers. They are interplanetary detectives designed to answer one question: could anything be alive down there? Europa Clipper will fly repeatedly through those plumes, its sophisticated instruments analyzing the chemical composition of the ejected ocean water. It will search for organic molecules, salts, and other compounds that would point toward a habitable environment. A positive result would be the strongest signal yet that we are not alone in the universe, that life may be a common phenomenon wherever the right conditions persist. Finding a second genesis of life, completely independent of our own, in the dark ocean of a moon would fundamentally reshape our understanding of biology. It would mean that life is not a rare, precious fluke confined to a single planet, but a natural, emergent property of the cosmos, ready to spark wherever there is water, energy, and the right chemistry. We would look up at Jupiter not as a distant point of light, but as the sun for a world that may be teeming with its own creatures, a reminder that the most profound discoveries in the universe may be hiding not on alien planets, but in the dark, silent seas of their moons. From solar flares painting our skies to the silent drift of continents in space, these 25 events form a timeline of cosmic wonder, a story unfolding from the immediate future to the distant eons ahead. We stand at a unique crossroads where the tools to witness these spectacles are finally in our hands. The sun's coming fury, the potential death of a neighboring star, the planned footsteps on Mars, and the slow, inevitable embrace of our galaxy with Andromeda are not isolated facts. They are connected chapters in the grand narrative of our universe, a story of creation, destruction, and relentless change. What makes this era so extraordinary is not just the scale of these predictions, but their proximity. For the first time in history, we are not passive observers of the heavens. We are active participants, sending probes to taste the waters of alien moons, building machines to listen to the birth of the universe, and preparing to become a multi-planet species. The pace of discovery is accelerating at a breathtaking rate, with each new telescope and each new mission rewriting the textbooks almost as soon as they are printed. This journey does not end when the final prediction is shared. It continues every single time you step outside and look up. That vast, star-filled canvas above you is alive with motion and possibility. It holds the answers to questions we have not yet even learned to ask. So keep looking up, stay curious. The greatest show in the cosmos is playing right above our heads, and your front row seat is waiting. If you want to continue exploring the universe's deepest secrets with us, subscribe for more journeys into the mysteries of the cosmos.